This is problem 5-84. It is on page 308. And in the problem, there's a beam that has two vertical sections, one horizontal section. What I've done is just gone ahead and drawn free body diagrams for each of the segments. And notice that the force applied is 125. The reaction forces are in the opposite direction, so we need a positive moment to keep that in equilibrium. Similarly, on this side, on the right-hand side, since the applied force is this way, the reaction force needs to be in the opposite direction, but since it's at a distance, we need a positive moment. Let's see, did I do that right? No. That needs to be the other way, right? There we go. So we need a negative moment. Let's see. We need a negative moment to hold the right-hand vertical segment still. Okay, so applying equal and opposite moments and forces to the center segment, this is what we end up with. This is just static, so let's work on the left-hand side. Summing forces in the y direction, we should get 0. That would be negative AY, because it points down, plus 125 pounds force multiplied by the sine of 20 degrees. And so from this we find out that the reaction force in the y direction, or the magnitude of that, is about 42.75 pounds force. Some forces in the x direction should be 0, and that would give us, let's see, what would we have? Well, we'd have negative AX plus 125 cosine 20 degrees, because there's a 20-degree angle there, okay? And so the x direction reaction is about 117.46 pounds force. Summing moments about A, taking counterclockwise to be positive, well then we're just trying to calculate the magnitude of that moment. We'd have a negative MA. Notice we're solving the free body diagram for this vertical segment, not for the bar yet. And then we'll have equal and opposite forces in moments. So MA plus what? Well, we're summing moments about A, and so the reaction forces won't come into play. And the vertical component of the 125-pound force won't come into play. Only the horizontal force comes into play. So that's a moment arm of 16 inches. That's this height, if you look at the problem statement, multiplied by 125 pounds force cosine 20 degrees. And so the moment, the applied moment from the horizontal segment onto the vertical must be 1879.39 inch pounds force. Okay, so now we've got the moments and reaction forces. Let me just write them down here, because of course they'll be equal and opposite. And I won't write the units. Hopefully from the context you'll understand what these things are. 42.75. So now we basically solved this side. That's all that they wanted us to do with that free body. And then finally we can write down AX, which is 117.46. Okay? So that takes care of the left-hand vertical portion of the beam. On the right-hand side, if you do the same thing, the procedure is exactly the same. It's just statics, and in the interest of time, I'm going to just write down the results, and I did write down the moments correct, so my results should be okay here. The moment at B ends up being 2,368.03, and of course the units here are inch-pounds force for all of the moments and pounds force for all the forces. I said I wouldn't write them, but I hate leaving the units off. The x component force, Bx, I found was 169.14 pounds force. And of course, technically speaking, this force is positive and that one's negative, but I just drew the directions of the arrows and left the sign in the arrow. So then By, I got 61.56, and of course that would be pounds force as well. Okay, so there are all of the loads applied to the beam. Okay, so now let's work on the beam segment. I called the distance from the reactions, because if you look at the picture, what you'll notice is there's a couple of X's on the beams. Those X's are where bearings are positioned, and according to the problem statement, there's no moments there. There's just forces that are perpendicular to the beam. And on the right-hand side is the only place where there's the ability for an axial force to be applied. Okay, in order, because notice there's an imbalance here between these axial forces. So one of the bearings has to take that load. This one takes it by the problem statement. I called the, let's see, 1879.39. I called the reaction at this bearing CY, and the reaction over here I called dy. Now, of course, there would also be a d sub x reaction to take care of this axial force. In fact, just summing forces in the x direction, you can find that the axial force dx, I'll write it over here, is just the difference between these two, right? Okay, so it comes out to 51.68 pounds force, and that's not really the focus of what we're doing here. What we're really interested in, so let's get rid of the stuff we don't actually care about. What we're really interested in is how these forces and moments affect the beam. But to get that, we have to figure out CY and dy. Now, we've summed moments and forces many times before. I'm going to work one of these. I'll sum moments about C to calculate dy, and then you can see that CY would be obtained the same way. For the sake of what I was doing, I called this L1, L2, and L3 because I like to work in symbols. That way, if I make a mistake, I can correct it easier. So summing moments about C, I shouldn't have erased all of my, let's see, what is this? This is AY, this is BY, and this was MA, and this was MB. Okay, anyway, let me move this down here. Summing moments about C, I should get 0, okay, but I have to apply MA. Okay, now again, if I take counterclockwise as positive, I'd have MA plus, this was MB, well, I've got it written there, plus MB, because it doesn't matter where those moments are applied, that's just the magnitude that's applied to the beam. Does everybody understand that and know that? Bless you. So, moment at A plus moment at B, that takes care of the moment pieces. We're summing moments about C. Well, AY is going to give us a moment, but it will be a negative moment, minus AY L1, right? So that's that moment. And then dy will give us a moment. That's the whole reason for writing this equation, because dy is the unknown. So dy multiplied by L2. So notice that's a positive moment about C. And then this by will give us a positive moment that is L1 or L2 plus L3 multiplied by dy. Okay? Now, again, I'm not going to go through all the details. You can look for these links in your book. They're all given. When I solved for dy, I found that dy was negative 191.51 pounds force. And using the same procedure, summing moments about D, to get the reaction force at C, I found that CY was 87.2 pounds force. It's 0.20 if you want to know for sure. Okay. Now when we sum all of the forces, we've got 42.75 plus 61.56 plus 87.2 less 191.51. The sum of forces in the y direction worked out, and it was correct. Okay. So now that this has gotten really messy, let me redraw this beam. I'm going to expand it a little bit. I guess I'll move it over here, and I'll just copy all of the forces onto it. So 42.75 and the moments as well. 1879.39. Let's see, next would be CY, so I'll give myself a little bit of space here. CY was 87.20. So to this point, let's see, we've got all of those. So we can get rid of that half. Just need a little bit of space. dy would be the next load, and it was negative, let's draw it this way, 191.51 pounds force. Since I drew it down, I took off the negative sign. And as we go out, then we're going to have the moment at the end. The moment was like this, and it is 2368.03. with 61.56 pounds at the end. Okay? Make sense? Hopefully this is a little bit clearer and easier to read than what I had a moment ago. Okay, the next thing to do then is to come up with the shear diagram, so let's do that. The shear will be measured in pounds force because all these are pounds force. And let's see. Do the moments affect the shear? Technically, yes. But when we draw the shear diagram, we've already taken into account the effects of the moments when we calculated the reactions. Does that make sense? So all we need are the y direction forces considered in order to come up with the shear diagram. So where should it begin? Well, it would begin at, let's see, let's put this down here, 42.75, because notice if we cut the beam here, we'd have to apply a positive shear to keep it in equilibrium. Okay? All right, so that would come over until this 87, so we move up by 87.2. That comes up to 129.95 pounds. Come down 191, that would bring us below the axis to negative 61.56. And fortunately, that brings us back to 0. That's what we expected. Okay? Got 4 minutes left. I think we can draw a moment diagram in 4 minutes, then you can go. The moment diagram is going to be measured in inch pounds forces. Are these inches or feet? Yeah, they're inches. Okay. Now, the moment diagram, this is where we'll have to be careful. Because there are moments applied to the end of this beam. In fact, the moment has to begin at 18.79, right? And notice, if we took a little segment off of here, there's a moment in this direction of this 1879.39 inch-pounds. Well, we'd have to apply a positive or negative? That's a negative moment, actually. Okay, so we'd have to apply a negative moment equal to that 1879. So we have to begin at negative 1879.39. Okay, that's where the moment actually begins in the beam. Well, then what? Well, then all we have to do is add up areas like we've done before. And these are fairly straightforward, simple areas. We don't actually have to integrate because they're easy. So 42.75 times the length, what is L1? Let's see, I jotted it down. Let's see, actually, this position measuring from the left is 16. There's 35 more, so that's 51. And then 67 are the X positions along this beam. Okay? Because there's 16 inches here, 16 here, and 35 here. So anyway, if you multiply 16 times 42.75, well then you're adding moment, right? The magnitude of the moment needed, the negative moment, it becomes less and less. So we need to move up. When I calculated this, please grab your calculator, multiply 16 times 42.75, and take that from 1879.39. What you should get is 1195.39 if I did my math right. Of course, this is a linear line. We're still on the negative side because we haven't had enough area to completely erase the negative moment. Anyone verify? Okay. The next thing I did is I said, well, now we've got more area here, 129.95, multiplied by this distance. Now don't multiply by 51, multiply by the difference between these two, which is 35. So 35 times 129.95, and take away 1195.39. When you do that, you should end up at 3,352.86. At least I hope you do, because that's where I ended up. Okay. In case the video cuts off, I'll just go ahead and tell you the next number. This area, notice this is a negative area, 61.56 times 16, so that will make me come down. I came down to 2,367.9, okay, which is pretty darn close to the moment at the end. Now I would suspect that I'd have enough round off here that those two are reasonably well agreed. Okay? So then notice that the moment on this end is like this, and that would take us back. Okay? The other thing we should do is calculate the location of this crossing. How would you do that? Well, you just need to calculate how much distance is needed times 129.95 to be 1195.39. Right? And that distance is the distance from here to here then. Okay? Make sense? I think we're out of video time. I'm sure it'll cut off in a moment, so we'll quit here. All right?